So let's just talk about the AVL tree. So the AVL tree is a self-balancing binary search tree. Here the height difference, or also we call the balance factor. So the height difference between the left and the right subtree is at most 1 for every node. So here we have one binary search tree. So here the tree is perfectly balanced. So to calculate the balance factor, so the balance factor is the height difference between the left and the right subtree. So height of the left subtree minus height of the right subtree. That is the balance factor. So in case of the AVL tree, the balance factor can be at most 1. So that means the balance factor can be -1, this can be 0, or this can be +1. So here in this case, if we calculate the balance factor for each of the node, so first of all for the node 5, so the left subtree has the height of 2 and the right subtree has the height of 2. So the balance factor will be 0. Similarly for the node 2, the left subtree has the height of 1 and right subtree has the height of 1. So the balance factor is 0. And for all the leaf nodes, the balance factor will be 0 because they do not have any child. For the node 8, the left subtree height is 1, right subtree height is 1, so the balance factor is 0. So because all the nodes have the balance factor within this range, so that means we can call this binary search tree as one AVL tree because the height of each node is balanced. Now there are certain advantages of using one balanced tree. So if we perform the insertion, deletion or the search operation, these operations will be much more efficient. These operations will have order of log n complexity because the tree is balanced. Now the same tree if the nodes are not balanced. So here we have the same binary tree with same nodes, but here the tree is skewed. So because the tree is not balanced, if we perform this insertion, deletion or the search operations, so these operations will have order of n complexity. So suppose you are searching for the node 7. So in the case where the tree is balanced, so here it will have maximum of 3 comparisons. But in case of this skewed binary tree, here we have to perform a total of 7 comparison, which is taking a lot of time, which is really inefficient. So when our tree is balanced, then it is taking logarithmic time to perform these operations, where in case of this skewed tree, the same operations is taking a lot of time. So with this self-balancing approach, we are making sure that our tree has the minimal height. So here in this case, you can see the tree has a very low height. Because of this, we have this logarithmic efficiency. So in case of the skewed tree, because the tree has a lot of height, which is the reason of this inefficiency. So with this AVL tree or the self-balancing tree, we are making sure that our tree has the minimal height. Now when the balance factor of any node goes out of this range, then we have to rebalance the tree. To rebalance the tree, we have to perform the rotation. So there are multiple rotations that we can do. So we can do the LL rotation, we can do RR rotation, and also we can do left right and the right left rotation. So in the next video, we're gonna see how we can perform all of these rotations to balance our binary search tree. So thanks for watching. See you in the next one. Take care.